Please subscribe to support the channel. Imagine holding a grain of sand between your fingers. Now imagine dividing that grain into 1,000,000 pieces. Take one of those pieces and divide it again 1,000,000 times. Keep going. Divide it 1,000,000,000,000 more times, then 1,000,000,000,000,000,000 times more. You still wouldn't be anywhere close to the Planck length. This incomprehensibly tiny scale, measuring approximately 1.6 times 10 to the negative 35th meters, represents perhaps the most profound frontier in all of physics. It's a realm so small that our everyday intuitions about space, time, and reality itself completely break down. Yet this seemingly abstract mathematical curiosity may hold the key to understanding the deepest nature of existence. To truly grasp just how small the Planck length is, we need to build a ladder of scales descending from the familiar into the infinitesimal. Consider your own body, standing roughly 2 meters tall. An atom, the building block of everything you see and touch, is about 10 billion times smaller than you. The nucleus at the center of that atom is 100,000 times smaller still. But here's where it gets truly mind-bending. The Planck length is smaller than a proton by a factor larger than the difference between a proton and the entire observable universe. Let me repeat that because it's worth sitting with for a moment. The jump from the Planck scale to a subatomic particle is more extreme than the jump from that same particle to everything we can see in every direction across billions of light years of cosmos. Another way to conceptualize this, if you could somehow magnify a single atom to the size of the entire observable universe, spanning 93 billion light years across, the Planck length magnified by the same factor would still only be about 10 centimeters, roughly the size of your hand. This scale is so removed from human experience that our brains didn't involve any intuition for it whatsoever. We can write the mathematics, we can manipulate the equations, but truly understanding what it means requires us to abandon almost everything we think we know about how reality works. Why does this particular scale matter so much to physics? Why have thousands of brilliant minds spent careers obsessing over something no one can see, touch, or measure directly? The answer is that the Planck length appears to represent a fundamental boundary in nature, the point at which the two great pillars of 20th century physics, quantum mechanics and general relativity, meet in a catastrophic collision. It's the scale at which space and time themselves may dissolve into something completely different from what we experience. Understanding what really happens at the Planck length isn't just an academic exercise. It's nothing less than an attempt to comprehend the ultimate nature of existence, to answer whether space and time are truly continuous or made of discrete chunks, whether the universe at its deepest level is smooth or grainy, analog or digital. The story of how we came to understand the importance of the scale begins not with space or quantum mechanics, but with something as mundane as the light bulb. In the late 19th century, physicists were grappling with a problem called black body radiation. When you heat an object, it glows, emitting light at different wavelengths depending on its temperature. Classical physics predicted that hot objects should emit infinite amounts of ultraviolet radiation, which clearly didn't happen and became known as the ultraviolet catastrophe. The equations describing light and heat were breaking down and no one understood why. Enter Max Planck, a German theoretical physicist who in 1899 was searching for a mathematical formula that would correctly describe the spectrum of light emitted by heated objects. Planck was a conservative scientist, deeply committed to classical physics, but he was driven to find a solution to this puzzle that had stumped his colleagues. In a move he later called an act of desperation, Planck proposed something radical. Energy couldn't be emitted or absorbed in any arbitrary amount, but only in discrete packets he called quanta. Energy, Planck suggested, was granular at the smallest scales, not continuous. This revolutionary idea required Planck to introduce a new fundamental constant of nature, now known as Planck's constant, which described the size of these energy packets. But Planck's genius extended beyond solving the black body problem. He realized that by combining fundamental constants that describe different aspects of nature, he could derive natural units of measurement that didn't depend on human conventions, like meters or seconds. By taking the speed of light, which governs the structure of spacetime, the gravitational constant, which describes how mass warps spacetime, and his new quantum constant, which described the graininess of energy, Planck could construct a characteristic length scale. The result was a number so tiny that it seemed to have no practical meaning, roughly 10 to the negative 35th meters. Planck himself didn't fully appreciate the significance of what he discovered. He thought of these natural units as mathematically elegant, but assumed they had little physical meaning. It would take decades and the development of both quantum mechanics and Einstein's general relativity before physicists began to realize that Planck had stumbled upon something profound. The Planck length wasn't just an arbitrary combination of constants. It appeared to mark the scale at which the quantum nature of spacetime itself would become important, the boundary beyond which our understanding of physics fundamentally breaks down. What Planck couldn't have known was that he had identified the battleground where the two greatest theories in physics would eventually clash. On one side stands quantum mechanics, our extraordinarily successful theory of the very small, which describes the behavior of atoms, electrons, and light with stunning accuracy. Quantum mechanics tells us that at small scales, reality becomes probabilistic rather than deterministic, that particles can be in multiple states simultaneously, that the act of measurement fundamentally affects what we measure. On the other side stands general relativity, Einstein's revolutionary description of gravity not as a force, but as a curvature of spacetime itself caused by mass and energy. General relativity has passed every experimental test we've thrown at it, from the orbit of Mercury to the detection of gravitational waves from colliding black holes. Both theories are triumphs of human intellect, arguably the two most successful scientific theories ever developed. Yet they fundamentally contradict each other when we try to apply them at very small scales and very high energies, precisely the conditions that exist at the Planck scale. Quantum mechanics treats spacetime as a fixed background stage upon which particles perform their probabilistic dance. General relativity tells us that spacetime is a dynamic, flexible entity that curves and flows in response to matter and energy. These two perspectives are incompatible, and the contradictions become impossible to ignore when we try to describe what happens to spacetime itself at the Planck scale. The mathematical problems that emerge are severe. When physicists try to calculate the quantum properties of gravitational fields at the Planck scale, the equations produce infinities, nonsensical results that suggest the mathematics itself is breaking down. These aren't the manageable infinities that appear in other quantum field theories, infinities that can be swept under the rug through clever mathematical techniques called renormalization. These are fundamental infinities that reveal a deep incompatibility between quantum mechanics and general relativity. The Planck scale marks the boundary of our current understanding, the point where the map of physical law simply reads, "Here be dragons." To understand why this clash occurs, we need to examine what each theory says about the nature of spacetime itself. Einstein's general relativity presents spacetime as a smooth, continuous fabric, like an infinitely flexible rubber sheet that can be stretched, compressed, and curved by the presence of mass and energy. When you drop a bowling ball onto a trampoline, it creates a depression, and if you roll a marble nearby, it will spiral inward along that curved surface. This is essentially how general relativity explains gravity. The Earth orbits the Sun not because the Sun is pulling on it with some mysterious force at a distance, but because the Sun's mass has curved the spacetime around it, and the Earth is simply following the straightest possible path through that curved geometry. This model of spacetime as a smooth continuum works spectacularly well at the scales we can observe and measure. It explains the precession of Mercury's orbit that puzzled astronomers for decades. It predicted that light from distant stars would bend around the Sun during a solar eclipse, a prediction confirmed by Arthur Eddington in 1919 and which made Einstein a global celebrity overnight. It predicted the existence of gravitational waves, ripples in spacetime itself traveling at the speed of light, which were finally detected by the LIGO experiment a century after Einstein first proposed them. At every scale we've been able to test, from the orbit of satellites around Earth to the dynamics of entire galaxies, general relativity's description of spacetime as a smooth fabric holds true. But what does it mean for space to be continuous? It means that between any 2 points in space, no matter how close together, there's always another point. You can always zoom in further, divide distances into smaller and smaller intervals, ad infinitum. It means that spacetime is infinitely divisible, that there's no smallest possible distance or shortest possible time interval. This is the assumption that underlies calculus and differential equations, the mathematical language in which general relativity is written. Einstein's field equations describe how the curvature of spacetime at each point is related to the matter and energy at that point, using the tools of differential geometry that assume spacetime is a smooth manifold. However, this picture of smooth, continuous spacetime may be fundamentally wrong at the smallest scales. As we approach the Planck length, quantum mechanics enters the picture with its characteristic uncertainty and graininess, and the smooth fabric of spacetime begins to look more like a violently churning sea. This brings us to one of the most profound and strange ideas in theoretical physics, a concept introduced by the physicist John Wheeler in the 1950s, known as quantum foam. Wheeler, one of the most creative minds in 20th century physics who worked closely with both Einstein and Niels Bohr, realized that quantum mechanics must eventually affect spacetime itself if we take the theory seriously at all scales. The key insight comes from Heisenberg's uncertainty principle, one of the foundational principles of quantum mechanics. Most people know the uncertainty principle in its familiar form. You cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure one, the less precisely you can know the other. But there's another version of the uncertainty principle that's equally important. You cannot simultaneously know both the exact energy of a system and the exact time at which it has that energy. The product of the uncertainties in energy and time must be greater than or equal to a tiny number, Planck's constant divided by 4 pi. This temporal uncertainty has profound implications for the vacuum of space. If we try to measure the energy of empty space at a precise moment in time, the uncertainty principle tells us that the energy must fluctuate wildly over short time intervals. These quantum fluctuations mean that empty space is never truly empty. For brief instants, particles and antiparticles can pop into existence out of nothing, borrowing energy from the uncertainty principle itself before annihilating each other and disappearing back into the void. These virtual particles are not just theoretical constructs, they have measurable effects. They cause the Casimir effect, where 2 metal plates in a vacuum are pushed together by the pressure of virtual particles. They alter the energy levels of electrons and atoms in ways we can measure with extraordinary precision. But Wheeler took this idea further. If quantum fluctuations can create particles out of empty space, they must also create fluctuations in space-time itself. The energy of these fluctuations has mass through Einstein's E equals mc squared, and mass curves spacetime according to general relativity. At large scales, these fluctuations average out and spacetime looks smooth, just like the surface of the ocean looks smooth from an airplane, even though it's made of countless moving water molecules. But as you zoom in closer and closer, approaching the Planck scale, these fluctuations become more violent and pronounced. The uncertainty principle ensures that at the Planck scale, quantum fluctuations in the geometry of spacetime itself become comparable to the size of spacetime you're examining. Wheeler envisioned that at the Planck scale, spacetime would resemble a foam or froth, constantly boiling with quantum activity. Tiny wormholes connecting different regions of spacetime would spontaneously appear and disappear. The smooth fabric of Einstein's spacetime would dissolve into a seething, chaotic landscape where the very notions of distance and duration lose their meaning. Space and time themselves would become probabilistic and uncertain. The topology of space would fluctuate, with the connectivity and structure of spacetime itself changing from moment to moment. This quantum foam would be the fundamental reality underlying the smooth spacetime we experience at larger scales. Much like the continuous flow of water emerges from the discrete motions of molecules, even though water at the molecular level looks nothing like a continuous fluid. The mathematical challenge of describing quantum foam is formidable. General relativity describes spacetime using smooth differential equations, but quantum foam would require a completely different mathematical framework capable of handling discontinuous probabilistic geometries. Various approaches have been proposed, from path integrals over all possible spacetime geometries to discrete models where spacetime emerges from the interactions of more fundamental objects. But without experimental evidence to guide us, physicists remain uncertain whether quantum foam is a real feature of nature or merely a suggestive metaphor pointing toward a deeper theory we haven't yet discovered. This brings us to a fundamental problem that has frustrated physicists for decades. We cannot actually measure anything at the Planck scale. This isn't just a matter of current technology being inadequate. There's a fundamental limit imposed by the laws of physics themselves. To probe smaller distances requires higher energy. This is why particle accelerators like the Large Hadron Collider, which smashes protons together at enormous energies, can explore physics at smaller length scales than previous experiments. The relationship is inverse. Doubling the energy of a particle beam allows you to probe distances roughly half as small. This is a consequence of quantum mechanics, specifically the wave-particle duality that gives every particle a wavelength inversely proportional to its energy. To probe the Planck length would require concentrating an enormous amount of energy into an incredibly tiny space. The specific number is called the Planck energy, approximately 1.22 times 10 to the 19th giga-electron volts. To put this in perspective, this is roughly the energy of motion of a small car traveling at highway speeds, but concentrated into a region the size of a proton. Creating such conditions would require a particle accelerator with a circumference comparable to the orbits of the outer planets, utterly beyond any conceivable technology. But even if we could somehow build such a machine, we'd immediately run into a more fundamental problem. At the Planck energy, something extraordinary happens. The concentration of energy becomes so intense that general relativity tells us it would collapse into a black hole. Let's walk through the paradox more carefully. Suppose you wanted to use a photon, a particle of light, to measure an object that's 1 Planck length in size. The wavelength of a photon determines the smallest distance it can resolve, much like how an optical microscope using visible light can't see individual atoms because atoms are smaller than the wavelength of visible light. To see something 1 Planck length in size, your photon would need a wavelength of 1 Planck length, which means it would need to carry the Planck energy. But here's the problem. General relativity tells us that any mass or energy, when compressed into a small enough region, will form a black hole. The amount of energy and the size of the region required to form a black hole are precisely related, and it turns out that a photon carrying the Planck energy focused into a region 1 Planck length across has exactly the right combination to form a black hole. So the very act of trying to measure what's happening at the Planck length would create a black hole that would swallow your measuring device and obscure the very thing you're trying to observe. This suggests that the Planck length might represent not just a practical limit on measurement, but a fundamental limit built into the structure of reality itself. It's as if nature has placed a veil over the deepest levels of reality, ensuring that we can never directly observe what's happening beyond a certain scale. The Planck length might be the universe's way of keeping its ultimate secrets. This measurement problem has profound implications. It means that any theory of Planck-scale physics cannot be tested through direct observation in the traditional sense. We can't simply build a better microscope or a bigger accelerator and take a look. Instead, physicists must rely on indirect evidence, mathematical consistency, and theoretical elegance to guide them. This has led to several competing theories about what really happens at the Planck scale, each offering a different vision of fundamental reality. The two most prominent approaches are string theory and loop quantum gravity, and they provide remarkably different answers to the question of what space-time looks like at the smallest scales. String theory emerged in the 1960s and 1970s from an attempt to understand the strong nuclear force. But it evolved into something far more ambitious, a potential theory of everything that could unify all forces and particles in nature into a single mathematical framework. The central idea of string theory is breathtaking in its simplicity and radical in its implications. Instead of treating elementary particles as zero-dimensional points, as we do in standard quantum field theory, string theory proposes that the fundamental constituents of reality are one-dimensional objects, tiny, vibrating strings. These strings are incredibly small, with a characteristic length right around the Planck scale. Just as a violin string can vibrate in different patterns to produce different musical notes, these fundamental strings can vibrate in different modes, and each mode of vibration corresponds to a different particle. An electron is one vibration pattern, a quark is another, a photon yet another. All the diverse particles we observe, from the lightest neutrinos to the heaviest quarks, would be different harmonics of the same fundamental string. Even gravity finds a natural place in this framework. One particular vibration mode corresponds to a graviton, a hypothetical quantum particle of gravity. This is remarkable because string theory automatically includes gravity, unlike earlier attempts to create unified theories that had to force gravity in artificially. The Planck length plays a special role in string theory. It represents approximately the length of these fundamental strings. At distances larger than the Planck length, strings look like point particles because you can't resolve their extended structure. This is why particle physics experiments, which probe scales down to about 10 to the minus 18th meters, still see particles as points. But at the Planck scale, the stringy nature of matter would become apparent. Space-time itself would look different at this scale because the fundamental objects have finite size. This finite size is what saves string theory from the infinities that plague attempts to quantize gravity using point particles. When you calculate quantum interactions involving gravitons in string theory, the mathematical infinities that appear in point particle theories are smoothed out by the extended structure of strings. String theory makes another stunning prediction that connects directly to the Planck scale: the existence of extra dimensions of space beyond the three we experience. In its simplest forms, string theory requires 9 or 10 spatial dimensions for the mathematics to be consistent. Obviously, we don't experience 6 or 7 extra dimensions in our daily lives, so where are they? The answer string theory provides is that these extra dimensions are compactified, curled up into incredibly tiny shapes at every point in space with size scales right around the Planck scale. Think of a garden hose. Viewed from far away, it looks like a one-dimensional line. But if you could zoom in close enough, you'd see that at each point along the line, there's actually a two-dimensional circle wrapping around the hose. In string theory, at each point in our familiar three-dimensional space, there would be an additional six-dimensional structure, but curled up so tightly that we can't detect it. These compactified extra dimensions are not arbitrary. They must have very specific geometries for string theory to produce a universe that looks anything like ours, with the right particles and forces. The possible shapes are called Calabi-Yau manifolds, exotic mathematical objects with beautiful and complex geometries. The particular way these extra dimensions are arranged determines what particles and forces appear in our three-dimensional world. Different Calabi-Yau geometries would give different physics, different particle masses, and interaction strengths. This creates both a strength and a weakness for string theory. The strength is that it provides a unified framework that could potentially explain all the particles and forces we observe. The weakness is that there are an enormous number of possible Calabi-Yau manifolds, perhaps 10 to the 500 different possibilities, leading to a vast landscape of possible universes with different physical laws. The Planck scale is where these extra dimensions would be directly observable, but as we've discussed, directly observing the Planck scale is impossible. This leaves string theory in a difficult position scientifically. It makes few testable predictions at the energies we can reach with current or even foreseeable future experiments. Some critics argue that string theory, despite its mathematical elegance and promise, has become more of a mathematical framework than a falsifiable scientific theory. Defenders counter that string theory has produced deep insights into quantum mechanics, black hole physics, and the mathematical structure of quantum field theory, even if we can't yet test its core predictions about the Planck scale directly. Loop quantum gravity takes a completely different approach to understanding the Planck scale. Instead of starting with particles and asking what they're made of, loop quantum gravity starts with space-time itself and asks how to apply quantum mechanics to the very fabric of reality. The theory doesn't assume that space-time is a smooth continuum. Instead, it derives from first principles that space must be quantized, built from discrete units when quantum mechanics is properly applied to general relativity. The Planck length emerges not as the size of fundamental strings, but as the characteristic size of the smallest possible unit of space itself. Imagine trying to apply quantum mechanics to geometry itself. In quantum mechanics, physical quantities like energy and angular momentum come in discrete units. An electron orbiting an atomic nucleus can only have certain discrete energy levels, not any arbitrary energy. Loop quantum gravity suggests that space itself behaves the same way. Just as energy is quantized, volume and area are quantized. There's a smallest possible non-zero volume of space and a smallest possible non-zero area. These minimum quantities are determined by the Planck length. A Planck volume would be a Planck length cubed, an almost inconceivably tiny amount of space. But according to loop quantum gravity, you cannot have a volume of space smaller than this fundamental quantum. The mathematical picture behind loop quantum gravity involves networks called spin networks. These are abstract graphs where nodes represent quanta of volume and edges represent quanta of area. Space emerges from the connectivity and labeling of these networks. As these spin networks evolve in time, they trace out structures called spin foams, which represent the quantum geometry of spacetime. In this picture, spacetime is not continuous, but fundamentally discrete and combinatorial, more like an intricate crystalline structure than a smooth fabric. At large scales, just as a large number of atoms appears to form a continuous material, a large number of these fundamental units of space would create the smooth spacetime we observe. One of the appealing features of loop quantum gravity is that it takes general relativity very seriously. While string theory modifies general relativity at high energies and introduces extra dimensions, loop quantum gravity tries to quantize general relativity in its original four-dimensional form, without adding new ingredients. The theory preserves one of the key insights of general relativity, that space-time is not a fixed background, but a dynamical entity that participates in physical processes. In loop quantum gravity, space is not just quantized, it's a quantum system itself, evolving and changing according to quantum rules. The Planck length in loop quantum gravity represents the fundamental grain of space, the pixel size of reality itself. Below the Planck scale, the very concept of distance would break down, because space itself is made of discrete units. Asking what happens at distances smaller than the Planck length would be like asking what happens between pixels on a computer screen when the pixels represent the fundamental reality. There is no between in a meaningful sense. This radical reconceptualization of space has profound implications. It suggests that space is not a container in which things happen, but an emergent phenomenon arising from more fundamental quantum relationships. Space as we experience it would be built up from something more primitive, perhaps from information or quantum correlations. Loop quantum gravity has had some striking successes in addressing problems that quantum gravity must solve. It provides a quantum description of black hole horizons that explains their entropy, the amount of disorder or information associated with a black hole in terms of the number of quantum states of the geometry at the horizon surface. This entropy calculation matches the famous Bekenstein-Hawking formula derived through semi-classical arguments. Loop quantum gravity also addresses what happens at the Big Bang singularity, suggesting that the infinite density predicted by classical general relativity is replaced by a bounce, where a previous contracting phase of the universe transitions through a finite maximum density into our current expanding phase. The Planck scale plays a crucial role in both phenomena, setting the scale at which quantum geometric effects become important. Nevertheless, loop quantum gravity faces significant challenges. Unlike string theory, it has not yet shown how to incorporate the standard model of particle physics, our successful theory of particles and forces other than gravity. It's fundamentally a theory of quantum geometry, and while it's clear that quantum geometry must be part of any complete theory of quantum gravity, it's less clear how matter and other forces emerge from this geometry. There's also the technical challenge of showing that the smooth space-time of general relativity emerges from spin networks in the appropriate limit, a problem that's mathematically difficult and not yet fully solved. Still, loop quantum gravity represents a radical and internally consistent vision of what might really happen at the Planck scale, space and time themselves dissolving into a discrete quantum structure. Both string theory and loop quantum gravity grapple with a bizarre idea that's emerged from multiple directions in theoretical physics over the past few decades. An idea that's so strange that even many physicists working on it find it difficult to fully accept. This is the holographic principle, which suggests that the fundamental description of our three-dimensional reality might actually be encoded on a two-dimensional surface, and that this encoding happens at the Planck scale. The name comes from optical holograms, where a three-dimensional image is encoded in a two-dimensional pattern. The holographic principle suggests that the universe itself might work the same way. The origins of the holographic principle lie in the study of black holes, which, as we'll explore more deeply shortly, have an uncanny connection to the Planck scale. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy proportional to the area of their event horizon, the boundary beyond which nothing can escape. This was puzzling because entropy usually measures the number of possible microscopic states of a system, and that number typically grows with the volume of the system, not its surface area. A black hole's entropy growing with area rather than volume suggested something profound. Maybe the information about what's inside a black hole is somehow encoded on its surface. Gerard 't Hooft and Leonard Susskind took this idea further in the 1990s, proposing that the holographic principle might apply not just to black holes, but to any region of space. The maximum amount of information that can be contained in any volume is not proportional to the volume itself, but to the area of the surface surrounding that volume measured in Planck units. A Planck area, 1 Planck length squared, can encode approximately 1 bit of information. This means that in some sense, our three-dimensional reality is a projection or representation of information fundamentally stored on a two-dimensional surface. This sounds like metaphysical speculation, but the holographic principle has received striking mathematical support from string theory through the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This correspondence shows that a gravitational theory in a particular kind of curved spacetime is mathematically equivalent to a quantum field theory without gravity living on the boundary of that spacetime, one dimension lower. The entire physics of the bulk spacetime, including gravity and the Planck scale structure of spacetime, can be described by a theory on the boundary that has no gravity at all. This is holography in action. The information about the interior is encoded on the surface. If the holographic principle is correct, and reality is fundamentally two-dimensional, with our three-dimensional experience being emergent or derived, what does this mean for the Planck scale? It suggests that the three-dimensional structure of space might not be fundamental. The discrete units of area on a holographic surface, each one 1 Planck area in size, might be more fundamental than the volume of space they encode. Distance as we experience it would be an emergent concept, arising from more fundamental relationships between bits of information on this holographic surface. Space-time itself would be a kind of illusion or approximation that works well at large scales, but breaks down at the Planck scale where the holographic nature of reality becomes apparent. The holographic principle connects to another deep mystery about the Planck scale: the relationship between quantum information and gravity. In recent years, physicists have increasingly come to believe that quantum information, quantum entanglement in particular, might be the key to understanding how space-time emerges. Experiments in quantum mechanics show that particles can become entangled, connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Recent work suggests that quantum entanglement between different regions might literally create the geometric connections we experience as space. Space would be stitched together by entanglement. At the Planck scale, where quantum effects dominate, this informational structure of reality would be exposed. Black holes provide perhaps the clearest window into Planck scale physics, even though they're among the largest and most massive objects in the universe. This connection between the cosmic and the infinitesimal is one of the most beautiful features of modern physics. Black holes are regions where gravity is so strong that space-time curvature becomes extreme, and it's precisely in these conditions that quantum effects at the Planck scale become important for understanding the system as a whole. Every property of a black hole is intimately connected to Planck units and Planck scale physics. Start with what's called the Schwarzschild radius, the size of a black hole's event horizon. This radius depends only on the mass of the black hole. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a supermassive black hole with 1 billion solar masses, it's about the size of our solar system. But there's a special case. A black hole with exactly 1 Planck mass, about 22 micrograms, roughly the mass of a flea egg. A Planck mass black hole would have a Schwarzschild radius of exactly 1 Planck length. This is no coincidence. The Planck mass is specifically constructed to be the mass where the Schwarzschild radius equals the Planck length, the scale where quantum gravitational effects become dominant. A Planck mass black hole represents a kind of fundamental unit, the smallest possible black hole that makes sense within our current understanding. You can't make a black hole lighter than this because quantum mechanics and gravity conspire to prevent it. Try to compress more energy into a smaller space to make a smaller black hole, and quantum uncertainty pushes back. The Planck mass emerges as the natural scale where gravity and quantum mechanics balance each other out. Black holes less massive than this would quantum mechanically decay almost immediately through Hawking radiation, a process where quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate. A Planck mass black hole would evaporate in about 1 Planck time, the shortest meaningful interval of time, about 10 to the power of negative 43 seconds. The entropy of black holes provides another crucial connection to the Planck scale. Bekenstein and Hawking showed that a black hole's entropy equals 1/4 of the area of its event horizon, measured in Planck units. For a solar mass black hole, this is an enormous number, about 10 to the power of 77, representing the number of different quantum states the black hole could be in that would look identical from the outside. This entropy must arise from some kind of microscopic structure at or near the event horizon, and that structure must involve physics at the Planck scale, because that's the natural unit in which the area is measured. Different approaches to quantum gravity provide different explanations for what this microscopic structure actually is. In string theory, the entropy can be accounted for by the number of ways strings can be arranged near the horizon. In loop quantum gravity, it's explained by the number of quantum states of the space-time geometry itself at the horizon surface. Both approaches require understanding physics at the Planck scale to explain black hole entropy, and the fact that they can reproduce the Bekenstein-Hawking formula is seen as evidence that they're capturing something true about Planck scale physics. Black holes also raise a profound puzzle called the information paradox that directly involves the Planck scale. According to quantum mechanics, information cannot be destroyed. The quantum state of a system fully determines its evolution, and you can in principle run the evolution backward to recover past states. But when matter falls into a black hole and the black hole later evaporates through Hawking radiation, where does the information about the matter go? The radiation appears to be thermal, containing no information about what fell in. This suggests information is destroyed, violating quantum mechanics. The resolution likely involves understanding the quantum structure of space-time at the Planck scale. The information must be encoded in subtle correlations in the Hawking radiation, correlations that depend on how quantum mechanics and gravity combine at the horizon, where Planck scale physics governs. The deepest connection between black holes and the Planck scale comes from the fact that black holes represent breakdowns of space-time itself. At the center of every black hole, general relativity predicts a singularity, a point where density becomes infinite and space-time curvature diverges. These singularities signal that our theory has broken down. We're extrapolating general relativity beyond its domain of validity. Physical singularities probably don't exist in nature. Instead, when we try to describe the region near a singularity using a complete theory of quantum gravity, the singularity would be replaced by some kind of Planck scale structure. Perhaps space-time terminates at a minimum length, the Planck length, beyond which the concept of distance ceases to make sense. Perhaps the violent quantum fluctuations of quantum foam become so intense that classical notions of spacetime completely dissolve. Understanding black hole singularities requires understanding the Planck scale. And conversely, black holes provide one of our best theoretical laboratories for studying Planck scale physics. Let's turn our attention now to what quantum field theory, our best theory of particle physics, tells us about the vacuum at the Planck scale. In the quantum world, the vacuum is never truly empty. This counterintuitive fact follows from the uncertainty principle we discussed earlier. Because you cannot simultaneously know the exact energy of a system and the exact time at which it has that energy, the energy of empty space must fluctuate. These fluctuations manifest as virtual particles, particle-antiparticle pairs that spontaneously appear out of nothing, exist for a fleeting moment borrowed from quantum uncertainty, and then annihilate back into nothing. Virtual particles are not just theoretical constructs, but have measurable effects. The Casimir effect, first predicted in 1948 and measured experimentally shortly after, demonstrates this beautifully. Place two uncharged metal plates very close together in a vacuum, and they'll experience an attractive force. Why? The plates restrict which wavelengths of virtual photons can exist between them, while all wavelengths can exist outside. This creates an imbalance in the quantum vacuum pressure that pushes the plates together. The Lamb shift, a tiny difference in energy levels of the hydrogen atom, arises from the interaction between the electron and virtual photons. These effects confirm that the quantum vacuum seethes with activity. But here's where things get strange. If we ask quantum field theory to calculate the energy density of the vacuum, taking into account all the possible virtual particles that can pop in and out of existence, we run into a catastrophic problem. The calculation suggests we should sum over all possible wavelengths of virtual particles, from the largest to the smallest. But what's the smallest wavelength we should include? Without a lower cutoff, the sum diverges to infinity, which is clearly wrong, since infinite vacuum energy would mean infinite gravitational curvature and no possibility for a universe like ours. So we need a cutoff, a shortest wavelength beyond which we shouldn't count contributions to the vacuum energy. The natural cutoff is the Planck length, the smallest scale where our current physics makes sense. When you use the Planck length as the cutoff and carefully sum up the contributions from all virtual particles with wavelengths longer than this, you get a prediction for the vacuum energy density. The number that emerges is approximately 10 to the 94th grams per cubic centimeter. This is an almost unimaginably enormous energy density. For comparison, the density of an atomic nucleus, one of the densest forms of matter we know, is about 10 to the 14th grams per cubic centimeter. The Planck scale vacuum energy would be 80 orders of magnitude greater. If this much energy actually existed in every tiny volume of space, the universe would have collapsed back on itself almost instantly after the Big Bang, or it would be expanding so rapidly that atoms could never have formed. The universe we observe would be utterly impossible. What's the actual vacuum energy density? We can measure it through observations of the universe's expansion rate and how that rate changes over time. These observations, particularly measurements of distant supernovae and the cosmic microwave background radiation, tell us that the vacuum energy density is approximately 10 to the minus 29th grams per cubic centimeter. This is extraordinarily small, barely above zero. It's so small that vacuum energy has only recently become important in the universe's evolution, driving the current acceleration of cosmic expansion we call dark energy. The vacuum energy is positive, but tiny. Now compare the theoretical prediction based on Planck scale physics to the observed value. The prediction is larger than the observation by a factor of about 10 to the 123rd orders of magnitude. This is not a small discrepancy. It's arguably the worst quantitative prediction in the history of physics, missing the mark by 123 orders of magnitude. Physicists call this the vacuum catastrophe, or the cosmological constant problem, and it represents one of the deepest mysteries connecting the Planck scale to the large-scale structure of the universe. Why is the vacuum energy so much smaller than Planck scale physics predicts? Several possibilities have been proposed. Perhaps there's some unknown symmetry that forces the vacuum energy to be exactly zero, and the tiny value we observe is due to some other effect. Perhaps in a complete theory of quantum gravity, the calculation that gives 10 to the 94th grams per cubic centimeter is simply wrong, and the correct calculation gives something much smaller. Perhaps we live in a multiverse with many different regions having different vacuum energies, and we necessarily find ourselves in one of the rare regions where the vacuum energy is small enough for life to exist, a kind of cosmic environmental selection. None of these explanations is satisfying, and the cosmological constant problem remains unsolved. It stands as a glaring indication that we don't understand something fundamental about how quantum mechanics and gravity combine at the Planck scale. This problem is sometimes called the worst fine-tuning problem in physics. It appears that the vacuum energy we observe must be the result of an incredible cancellation. The Planck scale contributions we calculated should be there, but they must be almost perfectly canceled by some other contribution we haven't accounted for, leaving only a tiny residual value. The cancellation would need to be accurate to 123 decimal places. Such exquisite fine-tuning seems implausible without some deeper explanation. It suggests that our current understanding of the vacuum and the Planck scale is missing something crucial, some principle or mechanism that we haven't discovered yet. The cosmological constant problem highlights a recurring theme in Planck scale physics. Effects at the smallest scale somehow influence the largest scales. The vacuum energy contributes to the cosmological constant, which determines the ultimate fate of the universe. Whether the universe expands forever or eventually collapses depends on the sum of all matter, dark matter, and vacuum energy. The Planck scale, incomprehensibly small, reaches out through the vacuum to affect the evolution of the cosmos itself across billions of light years. This connection between micro and macro is not unique to vacuum energy. The spectrum of fluctuations in the cosmic microwave background, the tiny temperature variations that eventually grew into galaxies and clusters, may have originated from quantum fluctuations stretched to cosmic size during cosmic inflation in the first fraction of a second after the Big Bang, when physics at energy scales approaching the Planck scale governed the universe's behavior. Just as the Planck length represents the smallest meaningful distance, there's a corresponding Planck time, approximately 5.4 times 10 to the negative 44 seconds. This is the time it would take light, traveling at the cosmic speed limit, to cross one Planck length. The Planck time represents something profound, perhaps the smallest meaningful interval of time, a fundamental quantum of temporal duration below which the concept of time itself breaks down. Our normal understanding of causality, the principle that causes precede effects, assumes that time is continuous and infinitely divisible. An event happens at some precise moment, causes propagate forward in time, and effects occur later at other precise moments. But if time is quantized, if it comes in discrete units of Planck time, then this picture needs revision. There would be no meaningful between two consecutive moments separated by one Planck time. Time would advance in discrete ticks like frames in a film rather than flowing smoothly like a river. At intervals shorter than the Planck time, the sequence of cause and effect might not be well defined. The very notion of before and after might become ambiguous or meaningless. This possibility has profound implications for physics. Most physical laws are formulated using differential equations that describe how systems change continuously over infinitesimal time intervals. If time is fundamentally discrete, at the Planck scale, these equations would be approximations that work well at large scales but break down at the smallest scales. We might need a completely different mathematical framework, perhaps something more like cellular automata, where the state of the universe at one tick determines the state at the next tick according to discrete rules. Some theories of quantum gravity, particularly certain approaches in loop quantum gravity and causal set theory, do indeed suggest that time is fundamentally discrete. The quantization of time raises the question of whether time is even a fundamental aspect of reality or whether it emerges from something more primitive. Some approaches to quantum gravity suggest that time as we experience it is not fundamental but emerges from timeless quantum correlations at the Planck scale. In these approaches, the universe at its deepest level is described by a quantum state that doesn't evolve in time because time isn't a fundamental variable. Time emerges as an approximate concept when we look at the universe at scales much larger than the Planck scale, similar to how temperature emerges as a concept when we look at large collections of molecules, even though individual molecules don't have temperature. If this view is correct, asking what happened at one Planck time versus another Planck time might be asking the wrong question. At the most fundamental level, there might be no time at all, only a web of quantum relationships from which the illusion of time's passage emerges. The connection between Planck units and time brings us to perhaps the most important application of Planck scale physics, understanding the beginning of the universe itself. According to the Big Bang theory, the universe began in an extremely hot, dense state and has been expanding and cooling ever since. As we extrapolate backward in time toward the moment of the Big Bang, the universe becomes hotter and denser, and the energy scales involved in particle interactions become higher and higher. Eventually, we reach energies comparable to the Planck energy and timescales comparable to the Planck time. This earliest epoch in cosmic history is called the Planck epoch. The Planck epoch lasted from time zero to approximately 10 to the negative 43 seconds after the Big Bang, 1 Planck time. During this brief interval, the temperature of the universe was around 10 to the 32nd Kelvin, hot enough that particle energies regularly reach the Planck energy. At these extreme conditions, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, had comparable strengths and may have been unified into a single superforce. The very distinction between particles in space-time would blur as quantum gravitational effects dominated everything. The smooth space-time of general relativity would give way to quantum foam, with the structure of space and time fluctuating wildly at each point. Our current physics simply cannot describe what happened during the Planck epoch. General relativity breaks down because quantum effects become crucial. Quantum field theory breaks down because we can't ignore the quantum nature of gravity. We're trying to describe a regime where quantum mechanics and general relativity both apply with full strength, and we don't have a theory that consistently combines them. It's as if we're trying to watch a movie, but the first 10 to the negative 43 seconds of footage is corrupted, and we can only see the film from that point onward. Everything we can say about earlier times is speculation, based on incomplete theories. Despite this limitation, physicists have developed scenarios for what might have happened during and immediately after the Planck epoch. One possibility, suggested by loop quantum gravity, is that the Big Bang wasn't actually the beginning of time, but a transition point, a big bounce, where a previous contracting phase of the universe reached a minimum volume set by the Planck scale and then rebounded into our current expanding phase. In this scenario, the infinite density of the classical Big Bang singularity is replaced by a finite maximum density, roughly the Planck density, about 10 to the 96 grams per cubic centimeter. Space itself, being quantized in loop quantum gravity, resists being compressed beyond this point, creating a kind of quantum pressure that causes the bounce. Other approaches suggest different pictures. String theory scenarios often involve higher dimensional spacetimes and brane collisions, where our universe began when two multi-dimensional surfaces collided in a higher dimensional space. The details depend on the specific string theory model, but the Planck scale again plays a crucial role as a characteristic energy scale where these processes occur. Still, other ideas propose that the universe emerged from a quantum fluctuation of nothing, with the Planck scale structure of spacetime allowing for the probabilistic creation of a tiny universe that then inflated to become our cosmos. What all these scenarios have in common is that understanding them requires understanding Planck scale physics. After the Planck epoch ended, around 10 to the negative 43 seconds after the Big Bang, the universe had expanded and cooled enough that quantum gravitational effects became less important, and physics we understand better began to apply. Grand unified theories, which attempt to unify all forces except gravity, become relevant. Slightly later, at around 10 to the negative 35 seconds, cosmic inflation may have occurred, a period of exponentially rapid expansion driven by a hypothetical inflaton field. This inflation stretched tiny quantum fluctuations in the inflaton field to cosmic sizes, creating the seeds of all structure we see today. Those quantum fluctuations originated at scales approaching the Planck scale, and so the pattern of galaxies across the sky might carry an imprint of Planck scale physics, encoded in the statistical properties of the cosmic microwave background radiation. Understanding the Planck epoch is crucial for answering the deepest questions about existence. Why is there something rather than nothing? Why does the universe have the particular physical laws and constants it does? How did time begin? All these questions lead us back to the conditions during the first Planck time, where the laws of physics as we know them break down, and something more fundamental must take over. Until we understand what really happens at the Planck scale, we cannot claim to understand the origin of the universe. This brings us to a question that physicists sometimes debate over late-night coffee or drinks. Is the Planck length actually real, or is it just a mathematical artifact, a sign of where our theories fail rather than a fundamental feature of nature? There are good arguments on both sides of this question, and the answer has profound implications for how we think about reality. On one side are physicists who believe the Planck length represents a genuine physical boundary in nature, a minimum length scale below which space itself has no meaning. In this view, space is fundamentally grainy or discrete, and the Planck length represents the size of the fundamental grain. Trying to probe distances shorter than the Planck length would be like trying to find positions between the integers on the number line when counting discrete objects. It's not just practically impossible, but conceptually meaningless. Space itself comes in Planck-sized chunks, and that's the end of the story. This interpretation is natural in theories like loop quantum gravity that explicitly quantize spacetime geometry. This view drops support from the measurement problem we discussed earlier. If it's impossible even in principle to measure anything at distances shorter than the Planck length because doing so would create a black hole, maybe there's a reason for this impossibility. Maybe nature is telling us that there's nothing there to measure, that distance simply doesn't exist below the Planck scale. The laws of physics would incorporate a fundamental minimum length, just as special relativity incorporates a maximum speed, the speed of light. Just as nothing can travel faster than light because space and time are fundamentally connected in a way that makes superluminal speeds meaningless, nothing can be smaller than the Planck scale because space is fundamentally quantized in a way that makes sub-Planck distances meaningless. On the other side are physicists who view the Planck length as primarily a marker of where our current theories break down, rather than a fundamental limit of nature itself. In this view, the Planck length simply represents the scale where quantum gravitational effects become important, and our current theories of quantum mechanics and general relativity, which are known to be incomplete, can no longer be trusted. A complete theory of quantum gravity might describe physics below the Planck scale perfectly well, perhaps showing that spacetime is smooth and continuous all the way down, or perhaps revealing some entirely different structure that our current theories don't capture. The Planck length would be like the sound barrier before we understood supersonic flight. It seemed like a fundamental limit until we developed better understanding and technology that allowed us to exceed it. In this view, the Planck length is less like a brick wall and more like a fog bank obscuring our view of what lies beyond. String theory tends toward this second interpretation, at least in some respects. While strings themselves are often said to be Planck length-sized, the theory can describe physics at shorter distances by considering higher energy string states and interactions. The theory doesn't prohibit arbitrarily short distances, but transforms what happens at those distances into different physics involving new vibrational modes and excited string states. Space-time at sub-Planck scales might look very different from what we expect, perhaps involving the extra dimensions becoming important, but it wouldn't simply cease to exist. There's also a more subtle intermediate position. Perhaps the Planck length is fundamental to our universe's structure, but not in a simple way. Maybe space-time is neither perfectly smooth nor perfectly granular, but has some more complex structure at the Planck scale that we haven't imagined yet. Perhaps the very question of whether distances shorter than the Planck length exist is ill-posed because distance itself is an emergent concept that only makes sense above the Planck scale. At the fundamental level, reality might be described by relationships that don't directly involve space and time at all. with space and time emerging from these more fundamental relationships only when you look at large collections of Planck scale degrees of freedom. This would make the Planck length the scale at which the emergent description begins to make sense, rather than a hard cutoff in some pre-existing space. The philosophical implications of these different interpretations are profound. If the Planck length represents a true minimum length, then the mathematical continuum, the set of real numbers where between any 2 points there's always another point, doesn't describe physical reality at the deepest level. Space would be more like the integers than the real numbers, countable rather than continuous. This would have implications for fundamental questions about infinity and the nature of mathematical truth. It would suggest that continuous mathematics, which has been so successful in physics, is ultimately an approximation to a discrete reality. Conversely, if spacetime is smooth all the way down, or if the Planck length is merely a limitation of our current theories, then the continuum might be physically real. The universe could be infinitely divisible, with structure all the way down to arbitrarily small scales that we simply haven't developed the mathematics or physics to describe yet. This raises different philosophical puzzles about how the infinite relates to the finite, and whether human mathematics can capture the true structure of reality. Given that we cannot directly measure what happens at the Planck scale, how can physicists hope to make progress? This question has become increasingly urgent as the gaps between the highest energies we can produce in accelerators and the Planck energy remain stubbornly vast. The Large Hadron Collider, the world's most powerful particle accelerator, reaches energies of about 10 to the 13 electron volts, impressively high by any everyday standard, but still 16 orders of magnitude below the Planck energy. Building an accelerator capable of reaching Planck energies would require a machine roughly the size of the solar system, an engineering impossibility for any foreseeable civilization. Despite this seemingly insurmountable barrier, physicists have developed clever indirect approaches to probing Planck-scale physics. These methods don't involve directly creating Planck energy collisions, but instead look for subtle effects that might propagate from the Planck scale up to scales we can measure. It's like trying to understand what's happening in the engine of a car by carefully measuring the exhaust, the vibrations in the steering wheel, and the performance of the vehicle. You can't see inside the engine directly, but if you're clever and your measurements are precise enough, you can infer a great deal about what's happening under the hood. One approach involves precision measurements of known particles and forces to look for tiny deviations from the predictions of the standard model of particle physics and general relativity. If Planck-scale physics involves new particles, new forces, or modifications to space-time structure, these might produce tiny effects at lower energies that we can detect with sufficiently sensitive experiments. For instance, if space-time has a granular structure at the Planck scale, photons traveling over cosmological distances might be affected in ways that depend on their wavelength, causing high-energy gamma rays to arrive at Earth slightly earlier or later than lower-energy photons from the same distant source. Observations of gamma ray bursts from billions of light-years away have placed stringent limits on such effects, constraining but not yet definitively ruling out various quantum gravity scenarios. Gravitational wave astronomy represents another promising avenue. The direct detection of gravitational waves from colliding black holes and neutron stars by LIGO and Virgo observatories opened a new window on the universe. As these facilities become more sensitive and new detectors come online, they might detect subtle effects in the gravitational wave signals that arise from Planck-scale modifications to general relativity. The in-spiral and merger of black holes probe extreme conditions where strong gravity meets high velocities and energies, potentially revealing quantum gravitational effects. While current detections are well explained by classical general relativity, future observations of smaller black holes or more exotic events might show deviations that point toward specific quantum gravity theories. Cosmic ray observations offer another indirect probe. Ultra-high-energy cosmic rays, particles from space that strike Earth's atmosphere with energies far exceeding anything we can produce in accelerators, occasionally reach energies approaching 10 to the 20 electron volts.
still below the Planck energy, but high enough that Planck-scale physics might become marginally important. Some theories predict that Planck-scale physics could modify the behavior of these extremely energetic particles in detectable ways, perhaps changing how they interact with the cosmic microwave background radiation, or altering the expected spectrum of energies we should observe. So far, cosmic ray observations have confirmed standard physics, but they continue to provide valuable constraints on Planck-scale theories. The cosmic microwave background radiation, the afterglow of the Big Bang, carries information about the universe when it was only 380,000 years old. But the patterns in this radiation, the tiny temperature fluctuations that eventually grew into galaxies, originated much earlier, possibly during inflation when energy scales approached the Planck scale. Detailed measurements of the cosmic microwave background by satellites like Planck have revealed a pattern of fluctuations remarkably close to the predictions of simple inflation models. But subtle deviations from the simplest patterns might encode information about Planck-scale physics. Features like primordial gravitational waves, which inflation should produce, would carry direct information from energy scales approaching the Planck scale. The ongoing search for these primordial gravitational waves in the polarization pattern of the cosmic microwave background represents one of our best hopes for learning about physics at the highest energies.
Perhaps most intriguingly, the study of black holes, especially the information paradox and the nature of Hawking radiation, might provide indirect evidence about Planck-scale physics without requiring Planck energy experiments. The resolution of the information paradox likely requires understanding how information is encoded in correlations in Hawking radiation, correlations that depend on the microscopic structure of black hole horizons at the Planck scale. Theoretical progress on this problem, combined with possible observations of small black holes that might exist as remnants from the early universe or could be created in exotic astrophysical events, might reveal crucial clues about quantum gravity. There have also been proposals for tabletop experiments that might probe quantum gravity effects. These typically involve trying to observe quantum behavior in increasingly large objects, or creating conditions where gravitational effects become important for quantum systems. For instance, experiments that create quantum superpositions of massive objects, or that try to detect the gravitational field of a single quantum particle, might reveal where quantum mechanics and gravity begin to interfere with each other. While these experiments wouldn't directly probe the Planck scale, they would test the interface between quantum mechanics and gravity, potentially revealing inconsistencies in our current understanding that point toward the correct quantum gravity theory. If spacetime is truly quantized at the Planck scale, a discrete structure underlying the continuous spacetime we experience, what would this mean for our everyday reality and our understanding of the universe? This question takes us into both physics and philosophy, challenging our basic intuitions about continuity, infinity, and the nature of the real. First, it's crucial to understand that any discreteness at the Planck scale would have absolutely no direct impact on our daily experience. The Planck length is so incomprehensibly small compared to any scale relevant to chemistry, biology, or human perception that quantized spacetime would be completely indistinguishable from continuous spacetime for all practical purposes. It would be like the difference between a digital photograph with 100 trillion pixels per square millimeter and a continuous analog image. To the human eye, they're identical. For all of chemistry, biology, engineering, and even most of physics, spacetime being grainy at the Planck scale versus perfectly smooth makes no measurable difference whatsoever. However, the implications for fundamental physics and our philosophical understanding of reality would be profound. If space is truly quantized, then motion at the most fundamental level wouldn't be continuous, but a series of discrete jumps from one space quantum to another. A particle wouldn't smoothly trace a path through space, but would hop between adjacent Planck scale positions. Time, being quantized, would mean that the universe evolves not continuously, but in discrete steps, each Planck time interval representing a single tick of a cosmic clock. The smooth motion we observe at large scales would emerge as an average over countless tiny quantum jumps, just as the seemingly smooth motion of a movie emerges from the discrete frames shown in rapid succession. This would fundamentally change how we think about Zeno's paradox, the ancient Greek puzzle about whether motion is possible if space and time are infinitely divisible.
Zeno argued that to cross a room, you must first cross half the room, then half the remaining distance, then half of what's left, and so on infinitely. Since you can't complete infinitely many steps in finite time, motion should be impossible. In continuous space and time, resolving this paradox requires sophisticated mathematics involving limits and infinite series. But if space and time are quantized, Zeno's paradox dissolves. There's a finite number of Planck-length steps from here to the other side of the room, and a finite number of Planck time steps in any finite duration. Motion simply involves moving through this finite sequence of discrete positions at discrete times. The paradox evaporates because infinite divisibility was an illusion. The relationship between mathematics and physics would need careful reconsideration. Calculus, differential equations, continuous functions, all the mathematical machinery that has been so successful in physics fundamentally assumes continuity. If space-time is discrete, then all these continuous mathematical structures are approximations. Extraordinarily good approximations at large scales, but approximations nonetheless. The real mathematics of nature at the fundamental level would be combinatorial and discrete, perhaps more like computer science and graph theory than traditional mathematical physics. We need to understand how the continuous mathematics emerges as a valid approximation when you consider many Planck scale elements together. Similar to how thermodynamics and fluid mechanics, which use continuous mathematics, emerge from the discrete behavior of atoms. Some physicists and philosophers have speculated that a universe with quantized space-time might be computable in a way that continuous space-time is not. In mathematics, there are different sizes of infinity, and the infinity of real numbers is vastly larger than the infinity of integers. A continuous universe contains uncountably many points and infinitely many bits of information, even in any finite region. A discrete universe with Planck-scale quanta would contain a finite number of degrees of freedom in any finite region, though that number would still be astronomical. This has led to speculation that the universe might be, in some sense, a computational structure, that physics is the algorithm and space-time is the data structure on which it operates. If this view is correct, understanding Planck-scale physics would be equivalent to understanding the universe's source code. The quantization of spacetime would also affect how we think about symmetries and conservation laws. In continuous spacetime, exact conservation of energy, momentum, and angular momentum follows from symmetries, continuous transformations of spacetime that leave physical laws unchanged. This connection, formalized in Noether's theorem, is one of the most beautiful results in physics. But if space-time is discrete, these symmetries can't be exact at the Planck scale because you can't continuously translate or rotate by arbitrarily small amounts. Conservation laws would emerge as approximate symmetries valid at large scales but violated by tiny amounts in individual Planck scale processes. Whether such violations could accumulate to produce measurable effects is an open question that different quantum gravity theories answer differently. Understanding the Planck scale has become central to one of physics' greatest quests, finding a theory of everything, a single unified framework that describes all particles and forces in nature, including gravity, from a single set of principles. This has been the dream of physicists at least since Einstein, who spent the last decades of his life searching unsuccessfully for a unified field theory. The quest has taken on new urgency and focus because it's now clear that any theory of everything must be, at its core, a theory of quantum gravity, a theory that tells us what really happens at the Planck scale. The need for unification arises from both practical and aesthetic considerations. On the practical side, our current theoretical framework divides physics into two incompatible pieces. Quantum field theory and the Standard Model describe three of the four fundamental forces with extraordinary precision, but treat spacetime as a fixed background. General relativity describes gravity beautifully as curved spacetime, but cannot accommodate quantum mechanics. This division works fine as long as we consider situations where gravity is weak and quantum effects are small, which covers most of the universe most of the time, but it fails catastrophically at black hole singularities during the Planck epoch and anywhere else both quantum mechanics and strong gravity matter simultaneously. We need a unified theory to understand these extreme situations. On the aesthetic side, the structure of physical law suggests underlying unity. The electromagnetic and weak nuclear forces, seemingly very different, were unified in the 1960s and 70s into the electroweak theory, showing their different aspects of the same force at high energies. The strong nuclear force, electromagnetic force, and weak force can be unified in grand unified theories, though these remain speculative. Gravity stands apart, but many physicists believe the separation is artificial, a result of our incomplete understanding rather than a fundamental feature of reality. At high enough energies approaching the Planck scale, all forces should have comparable strength and might reveal themselves as different facets of the single superforce. Finding this unified theory would represent the culmination of humanity's quest to understand the fundamental laws of nature. String theory offers perhaps the most developed attempt at such unification. By replacing point particles with extended strings and requiring mathematical consistency, string theory automatically includes gravity through graviton excitations and incorporates gauge theory similar to the standard model through different string states. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.